Let's solve some practice problems. Processing new accounts at a bank is intended to average 10 minutes each. 5 samples of 4 observations each have been taken. Use the sample data in conjunction with the information below obtained from the table to construct upper and lower control limits for both a mean chart and a range chart. Do the results suggest that the process is in control? For n equal to 4, that means we have 4 observation in each sample, and we have 5 samples here. A2 is given for you, the coefficients in the formula for n equal to 4, and D3 and D4 also are given. You have the table here as well, and you also have the formulas. So please pause, work on this problem, and then after you are done, come back to see the solution. All right, let's solve this problem. So we want to develop a control chart for the average, the mean, X bar, and also a range chart. For the average, we need to find the average of each sample and so also the range of each sample to do that. So let's find the average and the range. So we have 5 samples here, sample 1, sample 2, sample 5, 4, 3, and 4, and 5. And each sample has 4 observations. 1, 2, 3, and 4 observations. So let's see what is the average of the first sample, X bar 1. X bar 1 is, you sum up the observation, the 4 observation, that's 40 divided by 4, so that's 10. So the average of the first sample is 10. What is the range for sample 1? R1 is the maximum here minus the minimum. Maximum is 10.2, minimum is 9.8. So that's actually 0.4. So the range is 0.4. And then we're going to do this for sample 2, sample 3, sample 4, and sample 5. I'm going to skip sample 2, 3, and 4. I'm going to do another sample, which is sample 5. So X bar 5, the average of this fifth sample, is the summation of all these 4 observations, which is 40 divided by 4. That's all. Again, that's 10. It just happened by accident that the first and the fifth one have the equal actually averages. And then we find the range for the fifth sample. So the range is the maximum observation minus the minimum observation. So that's 10.3 minus 10.7, and that's 0.6. So range for sample 5 is 0.6. So we're going to have to also compute the average and the range for sample 2, sample 3, and sample 4 as well. So I'm going to actually type that out to have a neat data here. Here is our mean, the average, and range for each sample. The mean for sample 1 is 10, for sample 2 is 10.1, sample 3 is 9.9, 10.2, and 10. The range for first sample is 0.4, second sample is 0.6, 0.4, 0.6, and 0.6. So we have all the averages and all the ranges for all of the samples here. Now we can use the formulas to compute the control charts for X bar and for the range chart. So we need to compute the grand average, X bar bar. X bar bar is the average of averages. So that's X bar 1 plus X2 bar plus X3 bar plus X4 bar plus X5 bar divided by 5. And that's equal to 50.2 divided by 5, which is 10.04. 10.04. And for the range, average of range, we're gonna sum up all the ranges. So that's R1, which is 0.4, plus R2, which is 0.6, plus R3, which is 0.4, plus R4, which is 0.6, plus R5, which is 0.6. We sum these all up and divide them by 5, and we get 2.6 divided by 5, which is 0.52. Right, let me clear this up and type it out. So this is our X bar and the R bar, the average of range and average of averages. Now we can plug them in the formula for X bar chart and R chart to find the control limits for these two charts. For the X bar chart, the upper control limit for X bar chart is X grand average plus the A2, the coefficient from a table, multiplied by the average of range. So that's equal to 10.04 plus A2, which is 0.73, multiplied by the average range, which is 0.52. And that's equal to 10.42. For the lower control limit for X bar, that is grand average minus A2 multiplied by R bar. And if you plug in all the numbers, you're going to get 9.66. For the upper and lower control limit for the range chart, since D3 is 0, so that makes the lower control limit is equal to 0. And for the upper control limit, that's D4 is 2.28. So the upper control limit for R bar, that's D4 multiplied by R bar, and D4 is actually 2.28 from the table, multiplied by R bar, which is 0.52, and we get 1.19. And the lower control limit is just 0 because D3 is 0. So let me clear this up and type them out. All right, now that we have the upper and lower control limits for X bar chart, the mean chart, and the range chart, we can check and test whether the process is in control or not. For the mean chart, X bar chart, we're gonna see whether all of these sample means are within the control limit chart, control limits, whether or not. So the upper control limit is 10.42 and the lower control limit is 9.66. So as you see, all of these values are within these two range. None of them is outside of this range. So the process here is in control in terms of the central tendency or the X bar chart. Now let's see if that's also the case for the range chart. For the range chart, the control limits are between 0 and 1.19. And as you see here, none of these are outside of the control limits. So in terms of these two control charts, the mean chart, X bar chart, and also R chart, range chart, the process looks to be in control. Next practice problem. In checking several samples of credit card statements for errors, an auditor found the following. Each sample contains 200 statements. Each statements were either classified as erroneous or correct, or defect or correct. Calculate the two sigma control limits for this problem and determine whether it is in control or not. So you have the information given in this table. We have 4 samples, and in each sample there are 200 statements, and you see the number of erroneous statements or defective statements. So for example, sample 1 has 4 erroneous statements. That means it has 200 minus 4, which is 196 correct statements. You also have it for sample 2, sample 3, and sample 5. And also you get the formulas for a control chart for a C chart and a P chart here. Why this is not a mean chart or a range chart, the control limit, because this is not a variable. It's not a variable because it's not measurable. The number of erroneous, we can count them, but we cannot measure it. So please pause here, try to solve the problem. First, figure out whether this is going to be a C chart or a P chart, and then use the corresponding formula, the correct formula, to compute the control limits, the upper control limits and the lower control limits, and try to see if the process is in control or not. And then after you are done, come back to see the solution. All right, let's solve this problem. So first of all, this is going to be a P chart, a proportion, because you can count the number of erroneous statements, and also you can count the number of non-erroneous statements. For example, for sample 1, there are 4 erroneous or defective statements, and there are 200 minus 4, which is 196 correct statements. For sample 2, there are 2 erroneous statements, and there are 198 correct statements, and so on and so forth. So you can count the number of defective and the number of non-defective here. So this is going to be a proportion, a P chart here. So to be able to find the control limits here, since we don't have the proportion of erroneous statements in the population, we don't have P here, we have to estimate that using this formula here. So to do that, we need to find the percentage of defective for each sample. So for example, the percentage of erroneous statements for sample 1 is 4 out of 200. So that's 4 out of 200, which is equal to 0.02. 0.02. For sample 2, that's 2 out of 200, which is 0.01. And also we can compute it for sample 3 and sample 4. Let me clear this up and type them out. All right. So the percentage of erroneous statements for the first sample is 0.02. For sample 2 is 0.01, sample 3 is 0.025, and sample 4 is 0.045. Now we can find the average of percentage, the estimation of the proportion. So this is just an estimation, and that's going to be the total of number of defectives divided by 4. And we're gonna add these up and then divide them by 4. So that's 0.02 plus 0.01 plus 0.025 plus 0.045. Divide them by 4. And that's equal to 0.025. So our estimation of the proportion, in this example, proportion of erroneous statements is 0.025. That means 2.5% of statements are erroneous. We can also use this to find the standard deviation, estimation of a standard deviation, and that's equal to the square root of P bar, which is 0.025 multiplied by 1 minus 0.025, which is 0.975, divided by 200, the number of statements that we have, and that's equal to 0.011. Now that we have the estimation of the proportion and also the standard deviation, we can use these two formulas to compute the upper and lower control limits. The upper control limits is P bar plus Z multiplied by sigma, the standard deviation estimation, which is 0.011. And the problem asks for 2 sigma here, so this means that Z is equal to 2 here. So if you plug them in these formulas, we're gonna get the lower control limit as 0.003 or 0.3%, and the upper control limit as the 0.045, 0.047. Now let's check to see whether the process is in control or not. So we're gonna look for these proportion of each sample, erroneous statement in each sample, and we're gonna see whether these are within this range or not. So as you see, all of these values actually are within this range, all of them. So that means that the process is in control. This is the part B or version B of the same problem as we solved before, except that we now assume that the long-term fraction of erroneous statement or process measured over the past few years is known to be 2%. That means that we know based on the experience, based on the past data, that the percentage of erroneous statements is 2%. So we know the P here. So knowing the P now, how that would change your control limits. So please pause, try to solve this problem given the new information, and then see whether build a control chart, the control limits, the upper and lower control limits, and then try to see whether the process is in control or not. And after you're done, come back to see the solution. All right, let's solve this problem. So the only difference here that it makes here is that we know P. The proportion is based on the historical data. We know that it's 2%. So that means 2% of the proportion of erroneous statement is 2%. So we don't need to compute the estimation because we already have the P here. We can also compute the standard deviation of P. So that's P square root of P multiplied by 1 minus P divided by N, which is 200. And that's equal to a square root of 0.02 multiplied by 0.98 divided by 200, and that's 0.099. So that's 0.099. And if you plug them in these equations, you get the upper limit and lower limit for the control limits. So let me clear this up and type them out. So P is 2%, and sigma of P, the standard deviation, is 0.099. The lower limit is 0.002, and the upper control limit is 0.0398. Now, if you look at the data that we have here, based on this lower limit and upper limit, you see that all of these samples except the last one is within this range. 0.045 is actually greater than 0.0398, so it's outside of it's above the control limit, so it's outside of the control limit. This means that the process is not in control. The process is actually out of control. Next practice problem. A history professor is grading a midterm essay question. Aside from evaluating content, he has also decided to count the number of grammatical errors. So you have the information in this table right here. Suppose that he has 14 students in his class, and you can see in this table the number of grammatical errors that each student has made in his test, his or her test. So for example, the first student has made 2 grammatical errors, the second student has made 3, and so on and so forth. So we have it for 14 tests. First of all, you need to answer this question: what type of control chart should be used? And second is, what type of control chart should have been used if this was a multiple choice test of 10 questions instead of an essay question with grammatical errors? Because a multiple choice question, you don't get 2, 3, 4, 5 grammatical errors. There's no grammatical errors. It's either question is either wrong or right. Okay, so there is no number of errors. It's either erroneous or not erroneous. And third is create a control chart with the 3 sigma for this problem. So you have the formulas on the right. You have to decide whether this is a C chart or a P chart. And find the control limits and see whether the process is in control or not. So please pause, try to solve the problem, and then after that, come back to see the solution. So first of all, this is a C chart because we can count the number of grammatical errors, but you cannot count the number of non-grammatical errors. For example, student 1 has 2 grammatical errors, but we don't know how many. I mean, it doesn't even make sense to count the number of non-grammatical errors. Okay, unlike this scenario, which if we had a multiple choice question, if this was a multiple choice question and student 1 has 2 errors, that means that he got 2 questions out of 10 questions wrong. That means that he or she had 8 correct. So we could count both the erroneous and non-erroneous test here. But here in this situation, we have number of errors, grammatical errors. So we cannot really count the number of non-grammatical errors. So it's going to be a C chart here. All right. So since the average of error is not given here, number of errors, so we have to compute the C bar, the average of sample. So that would be C bar is equal to the average number of grammatical errors for all the tests. So that's 2 plus 3 plus 1 plus 0 plus 4 plus 0 plus 2 plus all of these. We add them up, divide them by the total number of tests for students. That's 14. And that is equal to 1.5. 1.5. Now we can use the formula for computing the upper control limit and lower control limit. So that's C plus minus Z multiplied by square root of C. Here we don't have C, so we're going to use the estimation C bar here. So if you plug in the value for C bar in this formula, we're going to get the upper control limit as 5.17 and the lower control limit as negative 2.17. Since we cannot have negative number of errors, we're gonna round it up or truncate it to 0. So the lower control limit is not negative 2.17, but it's 0, because that's the lowest number of possible errors. It's 0. So now that we have the control chart, we can see and determine whether the process is in control or not. If you compare actually all of these errors for these 14 tests, you'll see that all of them are actually within 0 to 5.17. So that means that the process is in control.